Good morning, everybody in San Diego. Thank you for attending, either physically or remotely. I am Thomas Evangelidis, live from Prague, from Europe. And thanks also to the organizers that gave me a 30-minute talk. I'm going to present you my algorithm for the first time in D3R challenge. And this presentation topic will be about application of artificial intelligence and quantum chemistry on binding affinity prediction. It will be divided in two parts. In the first part, I'm going to describe you my algorithm deepScaffOpt, which I developed myself, and it's suitable for affinity ranking. And on the second part, I'm going to describe you some recent attempts I did in the group that I joined last year to employ semi-empirical quantum mechanical methods to score for affinity and pose ranking. So I think in D3R challenges, the problem that we have to solve pertains to the lead optimization problem, where we have a few active compounds. We go to the synthetic chemist and we ask him to synthesize analogs of these compounds. But of course, the synthetic chemist doesn't have the time or resources to do all hundreds or maybe thousands of them. So we need a method to narrow down the list. Fortunately, we're living in the big data era where the public databases are growing up exponentially. As I show you on the left, the growth of Protein Data Bank, which provides the three-dimensional structures. And a similar growth has been observed for chemical databases like ChemPol, which provides almost 3 million chemicals with binding affinities and 2D structures. And of course, all this information can be utilized to train machine learning models. However, when you develop a machine learning model, special care must be taken to the loss function, for the loss function. Basically, the loss function is the heart of the machine learning algorithm and quantifies how well it predicts given the training data. In our case, the data, training data, are highly heterogeneous. They come from different types of assays. They may come from a cell-free assay like SPR, IPC, or FRET, or they may come from a cell-based assay, like flow cytometry. So a good loss function must treat differently the input data, depending on the type of the measurement, if it's a dissociation constant, for example, an IC50 or a percent inhibition, on the fact if it's a cell-free or cell-based assay, because cell-based assays tend to have higher errors in the measurements, and finally on the fact if it is a binding or a functional assay. In binding assays, we measure the binding directly of the compound to the target receptor, but in functional assays, we measure the biological effect. For example, the percent cell death in a cell line. All these factors must be taken into account by good loss function. In this slide, I show you several state-of-the-art neural network architectures. You see on the top left, the LSTM network, which is used for natural language processing. On the bottom left, you see the 3D convolutional neural network, which is used for pattern recognition in images. In the middle, you see a hybrid of them with allegedly better performance. And finally, on the bottom right, you see the autoencoder, which is used for dimensionality reduction and creation of samples with favorable properties. All these architectures, although they look very different between them, they share a common component. And this component is the fully connected layer. Actually, the fully connected layer can be an individual neural network, and it's called fit-for-one network or multi-layer perceptron. So the idea behind the development of deepScaffOpt was to use the multi-layer perceptron as a model network adapted to the problem of affinity prediction, push its capabilities to the maximum, and then be able to plug it in back to any type of complicated neural network architecture. In this slide, I show you an overview of the workflow followed by deepScaffOpt. Of course, the first stage is the expression of the molecules in a feature vector form, and this can be of various types, colored with different colors in this slide. Then deepScaffOpt, from each type of feature vector, it trains hundreds of multi-layer perceptrons. And then in the second stage, it filters out the bad predictors and keeps only 10 to 50 best predictors, and by employing a hacked random forest algorithm. And finally, in the third stage, it employs a network fuser, which will combine the best predictors and give you the final receptor-specific model, which will be able to read in the feature vectors of new molecules and return the binding affinity. The greatest advantage of this setup is that it can take an arbitrary number of feature vector types as input. Essentially, deepScaffOpt was designed to find on the fly the most suitable feature vector types for each system and combined in an optimal way. The main workforce behind deepScaffOpt in the latest D3R challenge were two types of two-dimensional ligand-based feature vectors. These were the 2D circular fingerprints and the 2D pharmacophore fingerprints. Both of them, they encode which substructures are present in the molecule, while the former, they encode the presence or absence of chemical substructures. The latter, they encode the presence of pharmacophore patterns. However, this consists only a very small fraction of all the available space of options that can be utilized with deepScaffOpt. For example, deepScaffOpt can be combined with LSTM neural networks, which process Miley strings as input, or undirected graph recursive networks, or various types of autoencoders, or generative adversarial networks, or even molecular neural graphs, as I will show you later, which are a special case of two-dimensional convolutional neural networks. But of course, the ultimate solution will be to be able to combine deepScaffOpt with 3D structure-based feature vectors like 3D pharmacophores. However, that necessitates the possession of an accurate post-prediction method, which I currently do not have. And in this slide, I summarize the functions that I use to generate the fingerprints. You can have a look afterwards. Most of them come from RDKit. One comment I have to make here is that in the D3R challenge of 2017, I also used 3D pharmacophores. However, I noticed that their performance was poor, and mainly because of the post-generation algorithm that I used. So in the latest challenge, I used only two-dimensional ligand-based feature vectors. And this is my first participation in the D3R challenge, was back in 2017. At that time, I had a very early version, an experimental version of my algorithm, which I called ScaffOpt, from scaffold optimization. ScaffOpt used only shallow neural networks, which were trained from compounds coming from a single binding assay. Notwithstanding with that very simplistic setup, I was able to do very well in cathepsin dataset, because it was the only dataset I had time to participate at that time. Actually, in the affinity ranking, I ended second, and in the second stage, and in the free energy dataset first. And that was a very good motivation to continue the development of ScaffOpt, which transformed to deepScaffOpt, that uses deep neural networks and all the available compounds from Campbell from that receptor. So once I had a stable version, I went back to all previous D3R challenge datasets, and I did a retrospective evaluation, starting from 2017 from cathepsin. With deepScaffOpt, which uses this time only two-dimensional ligand-based information, I was able to outperform myself and the top participant, which was from MolSoft. In P38 dataset, with deepScaffOpt, I was able to obtain way better predictions than the top participant. And in both cases, I marked with small icons the 2D-based methods and the ligand-based methods to distinguish them. So most of the top participants use three-dimensional information. Similarly for VGFR dataset, first position, outperforming mainly 3D structure-based methods. For FXR, first position, and finally HSP90 and MAP4K4, second and first position. These are all retrospective evaluation. I went further and compared deepScaffOpt with the performance of the widely used free energy perturbation model from Schrödinger. And I used the 8 protein ligand datasets from the publication as a blind test set. And as you can see with blue bars, with deepScaffOpt, I was able to obtain, in average, 43% improvement in Kendall-Stau ranking correlation, which is the most important metric in lead optimization. But let's go now to the D3R challenge, the recent one. In this challenge, we had two datasets, the one for base with 154 molecules, and one from cathepsin, 459 molecules, the largest I've ever seen. Both datasets contain molecules which have many heavy atoms, many rotatable bonds, as you see on the bottom, and many rings. However, the first dataset contains macrocycles, which makes the properties of these molecules different, as I will show you in the later slides. And these are the official results, first from the base datasets with the macrocycles. With deepScaffOpt, I was able to rank 13th in the overall rank. But as you can see, all ligand-based methods with circles have failed in this data set, and where deepScaffOpt was outperformed by 3D structure-based methods. Notwithstanding, in the second data set, which did not contain macrocycles, with deepScaffOpt, I was able to rank first with equal statistics with the second, or people from Molsoft. However, the rest of the top participants, they use 3D structures for their methods. Oh yeah, and also one comment about this, the result is that I have marked the top participants in the base data set, B1, B2, B3, and you can also see their performance in the cathepsin data set. And the majority of them did not do well. They did below the average in cathepsin data set, which means that these methods are not systematically accurate in every system. However, if I had, unlike deepScaffOpt, for example, which in base data set, although 13th is above the average, and in the second is the top. But if I had to choose a winner for this, or to be fair, I would choose the B3, which belongs to the group of Professor Guo Wei, whose presentation I'm looking forward to watch later. But now let's explain why all ligand-based methods have failed with the macrocycles. In order to understand that, we have to look carefully how the standard fingerprints are generated. In this slide, I show you how we generate the circular fingerprints. The input molecule in this slide is the pentamer ring, the triazoline, and the generation process begins by assignment of initial integer identifiers to each atom. These identifiers capture some local information about the corresponding atom in such a way that various atom properties like atomic number, connection count, etc. are packed into a single number, integer number, using a hash function. Then this integer number is projected to a bit vector with 1, meaning that the substructure is present in the input molecule, and 0, that it's absent. However, if you put a macrocyclic molecule as an input, the fragments that the algorithm looks for, given a diameter in bond length that is quite high, for example, as distinct fragments, they have completely different properties within the macrocyclic molecule than in a non-macrocyclic molecule. These, for example, methylacetamide fragments, they don't resemble nothing from the macrocycle. You can barely find where they are located in the macrocycle. And that's the main drawback, the main weakness of standard fingerprints. They encode each possible fragment completely distinctly, with no notion of similarity between fragments, neither of their chemical environment. So I was troubled by the low performance of ligand-based method, and I was seeking for an alternative representation. And I found the neural graph fingerprint. In that scenario, the molecule is represented not as distinct fragments, but as a graph, where each node of the graph represents individual atoms and the edges represent bonds. The lower layers of this network are 2D convolutional, in the sense that the same local filter is applied to each atom, but very importantly, also to each environment. So it captures also environment information for each atom. And of course, the last layers are a global pooling step that combines all the features and gives you the final fingerprint. So using the neural graph fingerprint with deepScaffOpt, I was able to jump from the 13th position to the 3rd. This, of course, the retrospective evaluation, because I didn't have time to implement it during the challenge. The code of neural graph fingerprint is open source, and I have uploaded it on GitHub. You're welcome to check it out. So in conclusion, deepScaffOpt does not require receptor or ligand 3D structures. It's fully automated, requires minor human input. It can screen compounds that span multiple chemical series, and it's extremely fast. It takes about 1 second per molecule once you have the model trained. But like every machine learning algorithm, the main drawback is that it requires training samples, which are not always available. My future plan for deepScaffOpt is to engineer a receptor-specific executable and give it to the user to be able to screen hundreds of molecules within a few hours. Future work also involves upgrade of deepScaffOpt to utilize 3D structure information, which is much wealthier. And I also create a new version, which I call a deep hit miner, that does classification of molecules to binders and non-binders. And it's more suitable for virtual screening. But now let's do a leap back to old school And let me describe you some semi-empirical quantum mechanical approaches to solve the same problem. As I already mentioned, last year, 1 year ago, I joined a group of Professor Pavel Hobza, in which they developed for over a decade their own scoring methods, which are based on quantum mechanics. In the traditional free energy approach, you break down the binding process into several steps, and you calculate the contribution of each step to the overall free energy of binding. These steps are protein and ligand dissolution, protein and ligand deformation in order to match each other, the complex formation, and finally, the complex resolution. I'm sure you're familiar with the steps from MMGBSA. And the equation that gives the overall score is shown in the middle. The first term is the interaction energy, free energy, which is calculated by PM6 or DFTB3 calculations with corrections for the hydrogen bonds, halogen bonds, and dispersion interactions. The second term is the dissolution free energy, which is calculated using the Cosmo-implicit solvent force field. Then there are the terms for the protein deformation free energy, the ligand deformation free energy, and finally is the entropy, the binding entropy, which has the conformational, the rotational, the translational, and vibrational components. However, because this term is very difficult and time-consuming to calculate, erroneously, as I will show you later, it has been neglected so far, and only the rest of the terms were used to calculate the score. The protocol that has been applied so far was the following, shown in this slide. Docking was conducted on a single receptor structure using various docking softwares. We generated hundreds of complexes. Then each complex was subjected to a subtle energy minimization, which introduced only small conformations to the receptor. In this way, the contribution of the protein conformational entropy to the final binding energy was minimal, so it could be safely ignored. And of course, the last step was SPM rescoring. This protocol has been applied successfully in the past in cases where receptor flexibility was not prominent, like in the problem of native redocking and native pose identification. Like in this slide, I show you the number of false positive poses scored first by widely used docking scoring functions from DOC, GlideXT, AutoDock4, and AutoDock-VINA, and finally, PM6 Cosmo and DFTB3 Cosmo methods. As you can see, the minimum number of false positives was yielded by the semi-empirical quantum mechanics methods, no matter if the system is charged, because as we know, in charged systems, charged cavities, molecular mechanics force fields and docking scoring functions, they are inaccurate, tend to be inaccurate. Another type of problem where quantum mechanics yields better results is metalloproteins, like the carbonic anhydrase, which is a zinc metalloprotein. We all know that accurate evaluation of metal-ligand interactions by docking or MD simulations currently is hampered by the complicated coordination geometries of the metal, and also by molecular mechanics force field inaccuracies. However, these weaknesses are not present in quantum mechanics method. That's why, using semi-empirical quantum mechanics, other members of the group were able to obtain R² of 0.7, as opposed to the next best correlation value, which was obtained by VINA, which was only 0.4. And the last case that I want to show you was HSP90. This is a special case again because the receptor has minimal flexibility. It also has a buried binding pocket, which is neutral. And the dataset, which was from DUD, the COI dataset, contained mainly similar compounds, which tended to be small and had an average net charge of 0. So all these characteristics, they facilitated rescoring either by MMGBSA or SPM. So what they did, the other members of the group, they were docking using 9 software, generation 700, 900 poses per compound, energy minimization, and then a filtering step using MMGBSA, which works well in the system with these characteristics. MMGBSA reduced the poses to 5 to 50 per compound, and that allowed effective, efficient PM6 Cosmo rescoring and final calculation of enrichment factors, which was very good. However, during MD simulations and minimizations, we all noticed that the general amber force field tool that we use is inaccurate and generates wrong geometries. So we devised a method for high throughput force field correction, which consists of geometry optimization of the ligand on the PM6 level of theory, measurement and copying the equilibrium bond lengths and angle from the optimized geometry, and either directly modifying the force field parameter files or applying restraints during the simulation. On the bottom, you see an example molecule, which was minimized with the default amber parameters, and next to that, the optimized geometry using the PM6. And as you can see here, the position of the protons in the sulfonamide substituent is completely wrong using the default parameters. And so is the orientation of the carboxy substitution, which should be perpendicular to the aromatic ring. So using these force field corrections, the other members of the group that did the study, they were able to obtain perfect enrichments and response rates. In this slide, I summarize the ROC curves for each alternative scoring function they used. The worst docking scoring function was that of Vina, colored with pink. The best docking scoring function was Glide SP with magenta. And surprisingly, although Vina had a very bad scoring function, the docking poses that the software generated were not that bad. And that can be reflected by the blue curve, which is the response rate of the docking poses of Vina upon rescoring using SQM Cosmo, which were better than those obtained from Glide, the best docking scoring function. But of course, the best results were obtained upon applying the force field corrections to the ligand force field, which are shown by the purple curve, and the response rate is almost perfect. The area under curve is almost 1. But okay, enough what happened in the past. Since last year that I joined the group, my task was to introduce receptor flexibility into the protocol. And this is the protocol I used in the D3R challenge. And I introduced receptor flexibility by applying an empty equilibration step upon the complex formation. However, this empty equilibration changes the final conformation of the receptor, not even between distinct ligands, but even between poses of the same ligand. And thus increases the contribution of protein conformational entropy into the binding, which I erroneously ignored because at the time the D3R challenge was running, as I will show you later. The post-generation algorithm that I used in the D3R challenge was not docking, but my own code, which I inspired during experimenting with a dataset of JAK2 from 2017. In that dataset, I had this compound 5, and I was looking for a crystal structure with a similar molecule, and I found this one. The only difference between these two molecules is para and meta substitution and the protonation state of this nitrogen. Otherwise, they're quite similar between them. So I was expecting to find a very homologous structure. However, I found a structure which shares only 35% sequence identity with JAK2, the target. But when I superimposed the two kinases, I saw that there was a complete overlap. They shared exactly the same fault, which was amazing. So I went on and created a homology model using the distant homolog, and then I replaced the similar ligand with a query ligand to generate the final complex of JAK2. And as you can see here, the two complexes, they have exactly the same, the ligands have exactly the same stabilizing interactions with a hinge region. So the algorithm which I named HomoligaLine was largely inspired by this publication, searches automatically for similar ligands in protein data bank. It searches for templates with similar ligands. It does homology modeling, then generation of multiple conformers of the query ligand and embedding of each conformer on the maximum common substructure of the crystal ligand. And finally, it selects the best conformer based on some energy and distance criteria and forms the final complex, which is subjected to empty equilibration afterwards and is ready for rescoring. So let's go in the recent D3R challenge. These are the two receptors that we had to deal with: the base protein, which has a buried and slightly negatively charged binding pocket, and cathepsin, which has a pocket which is exposed to the solvent and is neutral. And these are the official results from the free energy data sets, in which I participated both with deepScaffOpt, which is machine learning based, and with PM6 Cosmo, which is a free energy method, but at that time I included only the enthalpic term, not the entropic term. And as you can see here, according to Kendall's Tau, deepScaffOpt ranked at the 6th position and was outperformed by 3D structure-based methods, while PM6 Cosmo, which is a free energy method, ranked at the 12th position. In the other dataset, the cathepsin dataset, deepScaffOpt did worse, slightly worse, 9th position, outperformed by 3D structure-based methods. And to my pleasant surprise, the top participant used thermodynamic integration from the group of Carlos Zimmerling, if I remember correctly. However, in this dataset, in this system, the PM6 Cosmo enthalpic term did even worse than before, and the correlations were very bad, were almost zero. So I have to make 3 comments about these results. This is the cathepsin dataset, where in the affinity ranking of 459 compounds, deepScaffOpt was on the top. However, in this 39 compounds, which is a small subset of the whole pool, it ranked 9th. I presume the organizers, they selected them to facilitate alchemical transformations, right? So if we randomly select many times 39 compounds from the whole pool of 459, I think that the ranking will change. At least that's what statistics says. And deepScaffOpt, the overall performance will be better. The second comment I have to make is that looking at the results of PM6 Cosmo, the enthalpic term, in the 2 datasets, the base and the cathepsin, we can deduce that the conformational ligand entropy contribution to the binding is more prominent in the cathepsin dataset. And I believe that's because in the base dataset, we have the macrocycles, which are less flexible molecules than the acyclic molecules of the cathepsin dataset. And the third remark I have to make is that given the top participant is a free energy-based method, thermodynamic integration, the rapid development of artificial intelligence did not render free energy methods obsolete yet. So one last thing I tried was to replace the pose generation protocol I had with the poses from the top participants of base dataset, that was poses from Bogdan Yorga, and in cathepsin from Polo Lam, Max Dotrov. So I took the poses and I did rescoring with PM6 Cosmo, again using only the enthalpic term. However, I didn't notice any improvement in the overall ranking, which justifies my my comment that both systems, the entropic contribution is high, especially in the cathepsin dataset, which has more flexible molecules. So why did I describe all these diverse methods, homology modeling, machine learning, quantum mechanics? In this slide, I summarized the big picture, my future goal. My future goal was to introduce receptor flexibility into the free energy scoring protocol, either by using multiple crystal structures, or if it's not available, to use homology modeling to generate new structures of the receptor for ensemble docking. And then do MD equilibration, everything automatically, of course, and rescoring using PM6 Cosmo scoring function, but this time including the entropic terms and deformation energy, free energies. And that will hopefully increase the enrichment rate that I obtain, but most importantly, will increase the number of correct binding poses, which is necessary for the usage of 3D structure-based feature vectors in deepScaffOpt that will hopefully give the ultimate performance in this machine learning-based algorithm. So at this point, I would like to thank you for your attendance, for your patience. As I mentioned, deepScaffOpt is solely my creation, and I participated alone in this challenge. However, I would like to thank my friend Takayuki, who helped me with the implementation of neural graph fingerprint. I would also like to thank the SPM Cosmo team, my boss, Professor Pavel Hobza, Professor Jan Zezats, who developed the software that does quantum mechanics calculations, and finally Saltuk and Jamal. But I also would like to thank my second boss, Kostas Trixianis, because officially I have 2 jobs. My second job is about 4-dimensional NMR. We have developed a great algorithm, which is a game changer actually in NMR, and uses only 2 4-dimensional spectra to solve the structure of the protein in just 3 to 4 weeks. This is extremely fast with respect to other methods. We published the algorithm last year in Nature, and since then we published another 2 applications in Nature and many other papers. And we have also solved the structures of proteins spanning 13 unique protein folds, and these numbers keep growing. It's free software. You're welcome to check it out. So, and now I think we can proceed to the questions.
Thank you very much.
Yeah.
Thank you very much.
So we can try some questions.
Why don't I try to repeat it? Why don't you stop up there?
Yes, try to repeat the question.
That's a good idea.
Hi, Thomas. Can you hear me?
Yes, I can hear you clearly. Hello.
So I was wondering if you could tell me a little bit more about your training method. Are you doing like some kind of, are you doing supervised pre-training on the target of interest in Chembl using Chembl data, and then, sorry, and then transfer?
Yes.
So are you doing
learning.
semi-supervised pre-training on Chembl and then transfer learning on the data set that GC provides? Or are you augmenting the GC data set with data Chembl and training all in one go? Have you looked at the scenario where you don't actually use the data set provided by GC for training and just make predictions directly using data from Chembl?
All right. What I do is using only data from Chembl. But I apply special filters at the beginning because, as I showed you in the slide, the loss function of deepScaffOpt, which I think it's half of the success of the algorithm, it's very specific. It's multi-component and very specific. It takes into account the source of each experiment and the type of each experiment. So special parsing of Chembl data precedes the training. Regarding transfer learning, yes, I tried that, but I think for the results were disappointing, and I think for the problem of affinity prediction, unlike for toxicity prediction, all the kinds of problem, it's not so good. It's not a good solution.
Thank you.
So yes, did I answer your question, or still something missing?
You answered it. Thank you.
You're welcome.
Hi, this is David Min from Illinois Tech. I'm asking about, you showed some results about the performance of SQM Cosmo in pose rescoring from the past and showed that it was positive compared to docking scores. What do you think the secret ingredient or the ingredient that's missing from the docking score could be that would lead it to not perform so well as SQM Cosmo? Do you think it's like the solvent model? Do you think it's like polarization of the ligand, or what? Any other factor that could be?
Yes. The factors that you mentioned, they play a great role in the results. In general, we have observed that in charged system, polarized system, when I say polarized, I also mean charged binding cavity or polarized ligands. The docking scoring functions, they tend to produce inaccurate results. So the description of the atomic structure is inaccurate. But however, most of the docking scoring functions are either empirical or knowledge-based. At least apart from Autodoc 4, I think, which is more physics-based, the rest, they tend to include other terms which compensate for the entropic contribution of the solvent, or entropic contribution of the ligand or the protein, etc. And I think, like in every scoring function, there's not one single function which is systematically good in every receptor and decoy set. So there are always pros and cons. However, from this trend, at least for post-prediction, and also with metalloproteins, with the special cases, the coordination geometry of the metal is very difficult to capture correctly by docking scoring functions. These systems can be treated better by semi-empirical or quantum mechanical description of the protein and ligand, the atoms. So I think that when producing the companies that produce the token software, they're looking for a fast solution. And this quantum mechanical rescoring is very time consuming, requires a lot of computer resources. However, in our hands, it tends to give more accurate results. So I don't think the token scoring functions will evolve that much that will beat the quantum mechanical scoring.
Okay, thanks.
At least in the special cases, I'm sorry, just to add something. At least in the special cases where receptor flexibility is not so prominent, so the entropy contribution is not that big.
Hi. So I have two questions. So first, you mentioned about splitting this data depending on the type of the assay. Did you actually use IC50?
Yes.
Because for IC50 or EC50, there are a lot of uncertainties about the experiments. And it is, I think in machine learning field, it's known that fitting with IC50 is quite risky. And the second question is, so this 2D fingerprint-based method, it is very easy for neural network or random forest to memorize the bit vector, especially if you're trying to use Campbell data set. There are a lot of clusters from the same experiment groups. So this machine learning method try to memorize the molecules from the particular group rather than trying to generalize the physics. Did you use any like special treatment for avoiding this overfitting or bias problem? Thank you.
All right. In the first question, you're absolutely right. IC50s and EC50s and the rest of the measurement types tend to be more inaccurate than KD or KI. And that's because KD and KI are protein concentration independent. In IC50, for example, if the minimum concentration in the assay is 10 nanomolar, the minimum IC50 value that you can get from the ligand is 5 nanomolar. So because of that protein concentration dependence, even in protein different, let's say the same binding assay, for the same system, the same ligand, the same protein, if it's conducted with slightly different protein concentration, you get different IC50 values. And that is taken into account by the loss function. The loss function is clever enough to distinguish that. So I cannot disclose more details about how it calculates all these differences and what are the terms of the loss function, because I haven't published the method yet. But yes, you're right, and it takes into account. Also takes into account that cell-based assays are more erroneous, have larger errors than cell-free, and also the functional assay is the same. Now going to the second question, the random forest. The random forest in this context of deepScaffOpt, first of all, it's hacked. It's not the original implementation you can find in scikit-learn, for example. It's hacked in the sense that instead of returning feature importances, it returns network importances. So it was designed so that to quantify the importance of each multi-layer perceptron of the hundreds that it gets as an input, and keep those 10 to 50 that have the top importance. And these are usually the best predictors, and that is done by a type of cross-validation. And why did I use random forest? Because from all machine learning algorithm, as you also mentioned that, it tends to be less prone to overfitting. And because basically I do this by cross-validation, something I can't disclose more details, the test set is very small. So I had to select an algorithm that is less prone to overfitting. So that's the most I can tell you until now. I'm sorry.